Welcome to Lecture 10 on Robot Dynamics. This lecture will focus on rotorcrafts and specifically about the modeling and control of quadcopters. I'm Roland Siegwart, I'm the teacher of this lecture. This lecture is divided in three segments. We will start with an introduction and then go into depth about the modeling of quadcopters. This will continue then with the control of quadcopters, and at the end we will see how we can calculate the thrust force generated by propellers and rotors. Even if the first rotorcraft lifted from the ground about 90 years ago, they are still less used than fixed wing today. Rotorcrafts are wonderful to search and rescue people, to transfer goods in a very difficult and narrow environment. This comes from their advantage that they are very agile. They can hover at different spots very precisely, and they have, of course, the ability to vertically take off and land. On the other side, their machines, rotorcrafts, are very complex and in consequence need high maintenance costs. They are also more risky if you have, for example, a failure of a motor, and especially they have a very poor efficiency in forward flight, but also in all different operations. Rotorcrafts have become very interesting recently in the development of very small unmanned air vehicles, because there they can actually fulfill tasks which you cannot fulfill with a fixed-wing airplane. Typically we distinguish three different types of rotorcraft. The first one is the helicopter, which is the most standard one and typically used in most applications. It has a main rotor which is tiltable, and by tilting and adapting the main rotor and its blade angle, you can generate uplift and also forward speed. In this concept, the flow of the air is actually going from top to bottom. A more exact solution is the autogear. The autogear has a main rotor which is not propelled, but the propulsion or rotation of the main rotor is generated by the forward propulsion of the whole system, so you need an additional propeller. The main rotor then automatically generates an uplift similar to a wing. The airflow in this case is from bottom to top, and of course this system has then no capability to hover, and so it hasn't really the nice advantage of a rotorcraft, a typical rotorcraft. The third one is a gyrodyne, which has a main rotor which is not is actuated around its main axis but not controlled in angle. So the main rotor cannot tilt and thus also not generate forward speed. So in this concept, the forward speed is actually generated by an additional propeller which actually pushes the whole rotorcraft forward, and similar to the helicopter, here the airflow is from top to bottom. Helicopter rotorcrafts can come with different number of main rotors. The single rotor helicopter is the most efficient. However, it has a limited payload and it needs additionally a tail rotor to counterbalance the torque generated by the main rotor. Multi-rotor helicopters can be arranged with two or even more main propellers. They have a reduced efficiency because of the downwash on interference of the main propellers with the body and with each other. On the other side, they can actually lift higher forces and therefore they are often used for carrying big payloads. If multi-rotor rotorcraft have an even number of rotors, they need actually not a tail rotor for counterbalancing. In this lecture we will focus on so-called unmanned air systems, and especially in very small unmanned air systems which are typically called micro-air vehicles. One example of these type of system are quadcopters or quadrotors or multicopters. They have typically 4 or more propellers in a symmetric arrangement. They have motors which don't have gearboxes to directly propel the main rotors and propellers. They have a very good torque compensation because of their symmetry. They are very maneuverable and agile, so they can move very fast and dynamic in all environment. This high dynamics, on contrary, actually needs a very dynamic control and very precise measurement of the attitude and forward speed. In contrast, the standard helicopter, which still also exists for unmanned air systems and micro air vehicles, they are more efficient. On the other side, they need a more complex mechanism to control the cyclic pitch, the swash blades of the main rotor. They require a tail rotor. They have lower dynamics and lower agility, and they are much more difficult to scale down. So if you want to go really in a system which has probably rotor diameters of 10 or 15 centimeters. So in applications, you still see more or less the standard helicopter as unmanned air systems, but in sizes which are still probably a weight of a couple kilogram and above. And quadrotors you can see in all different sizes, from bigger systems but mainly for very small systems, the smallest having roughly only about 10 centimeters in diameter, including the 4 propellers. However, there exist many different concepts for UAVs and MAVs. For example, ducted fans. In a ducted fan, you have typically 2 counter-rotating fixed propellers, and then the control surface is able to control the systems in all flight directions. These systems on one side are compact and automatically protect the propellers. On the other side, they are heavier than standard helicopters or multicopters. Another interesting arrangement is coaxial helicopters, which have 2 propellers on top of each other, more or less on the same axis. This allows to have a counter rotation of the 2 propellers, and you don't need to counteract on the torque. They are, in consequence, actually passively stable. So in principle, without a lot of control, you can have it very stable in the air. But the mechanism to control actually the main propeller to get forward and backward speed is somewhat complex. They can be compact, but and then especially because they are passive and less stable and less critical to control, they are well adapted for very, very small UAVs. The most recent concept of small unmanned air vehicles are so-called omnidirectional multicopters. These systems, they have 4 and more main propellers, but in contrast to standard multicopters, they can actually rotate their propellers around against the main body. By doing so, they can fly actually in all directions with any attitude of the main body. Furthermore, this allows us to generate forces in all directions and thus get in interaction with the environment. Of course, these systems have a little bit more complex control and have some interference between the propellers which blow into each flow. However, by using these systems, you can actually generate very new applications. As you can see here in this video, these omnidirectional helicopters can fly in rotation without actually moving in translation, or move in translation without changing the attitude of the body, which is actually done with a system which has no rotation of the main rotors. So by doing so, you can attach a pen to a flying platform and then write on a whiteboard by just generating normal forces against the whiteboard and then move precisely laterally to the whiteboard. This is only possible due to this omnidirectionality of the system, and this shows what new potential these flying platforms can open for applications. After this introduction to rotorcrafts, we would like to go over now to the modeling of a rotorcraft, in a specific case, a quadcopter. There are 2 main reasons for dynamic modeling. On one side, you would like to analyze the systems. The models allow you to evaluate the characteristics of the future aircraft in flight or in behaviors in various conditions, even before the rotorcraft is built. It allows us to say something about stability, the controllability of the system, about power consumption, and much more. On the other side, in order to design the control loops, you need simulations, because if you want to do this directly on a built rotorcraft, you put the whole rotorcraft in danger. So the model allows you to compare various control techniques and tune the parameters. It helps you to gain money and time, and as mentioned, it will not put your system in risk. Modeling and simulation are very important, but in most aircraft you still need also the validation in real systems. Before we start to develop the model of a quadrotor or quadcopter, we have to be clear about the assumption and simplifications we take for the modeling. We first assume that the center of gravity coincides with the body frame origin, so meaning that it is exactly in the center of the four propellers. We further assume that there is no interference with ground or other surfaces. We assume that the whole structure is symmetric and rigid. We assume also that the propellers are rigid and the fuselage has no influence on the propeller thrust. Of course, these assumptions will actually result in a not absolutely precise model, but in reality has shown that most of these assumptions are valid enough then to still have a good model for controller layout. Dynamic modeling of quadrotors is quite comparable with other dynamical systems and robots. We have in this case three blocks: motor dynamics, aerodynamics and body dynamics. First, the controller gives a desired speed, rotational speed of the main rotors. The motor dynamics allows you to calculate the real speed of the motor at any given time. This speed in context with the propeller and the aerodynamics then generates the forces and torques, which are then as the next step acting on the body. These forces will then generate accelerations and rotational accelerations, and by integrating them you will have the motion of the main system. So in order to model the whole system, you have to have a closer look in all three parts. Of course, the most important and crucial part is the body dynamics, and therefore we will actually start with the body dynamics of a quadrotor. For the quadrotor, we start again with the general formulation of the multi-body dynamics, as you have seen it already before. So we have all the different forces acting on your system. On the very left, you have the mass matters multiplied by the accelerations. Then you have the centrifugal and Coriolis forces and the gravity force, and of course then all the forces externally or by the controller and rotors are acting on the system. Based on this basic model, you can now develop, based on the geometry and the masses and forces of a quadrotor, elaborate the dynamic model of a quadrotor. A quadrotor can be modeled as a rigid body with four propellers arranged symmetrically at their corners. Each of the rotors, together with their motors, generate a force and torque acting on the entire system and allowing to control the quadrotor in the free space. These four forces and torques generated by the rotors can then be combined to a single force and torque vector acting at the center of the rigid body of the quadrotor. In order to describe in the dynamic model the motion of the helicopter, additionally we need of course an earth coordinate system and a body coordinate system, which is typically aligned with the center of the quadrotor. This will later on allow us to control the system in free space in a very dynamic and agile way. This is, for example, useful if you want to use quadrotors to play ping pong. This is a work which was done by my colleague and his team at ETH, Raf de Andrea, and shows that by very dynamic and precise control of quadrotors, you can play ping pong, or you could, for example, also balance a stick on the quadrotor. Furthermore, for establishing the dynamic model of the quadrotor, you need, of course, the whole geometric information about the system. So the arm length, which are typically symmetric, measured from the center of the whole system. You need the distance or the height of the propellers above the center of gravity. You need the total mass of the whole system, and you need the inertia around the x and y axis, which are typically assumed to be symmetric. Typically, we have four forces or moments generated by a propeller of a rotorcraft. The thrust force is the force which generates the lift to keep the rotorcraft in the air. The drag torque is the rotor drag and defines the required motor power to keep the rotorcraft in the air. Additionally, we have the hub force and rolling moment. They depend on the flight regime, mainly on the forward speed of the quadrotor. In our case, we are looking at the quadrotor model around hover condition. In hover, hub force and rolling moments are very small compared to thrust and drag moments, and they can therefore be neglected. Furthermore, thrust and drag are, in a first approximation, proportional to the propeller's squared rotational speed. Therefore, the thrust can be calculated by the thrust constant multiplied by the rotational speed of the rotor, and the same is for the drag. The drag moment is proportional to the speed of the propeller squared. We will have more details about propeller forces in a later section of this segment. In order to establish the dynamic model of the rotorcraft, you have to find the relation between the Earth coordinate system and the body coordinate system. This is typically given by 3 rotation around 3 different axes. In the context of rotary wing, but also fixed wing, these axes are typically selected as followed. First, you have a yaw rotation. This is a rotation around the z-axis of the Earth coordinate system. Then you have a pitch rotation around the y-axis, and then you have the roll around the x-axis. It is well known that in order to find the rotation from the body frame to the Earth frames, or vice versa, you have to just calculate the individual matrices for yaw, pitch, and roll in a sequence. The rotational velocity in the body frame is given by the sum of the rotational velocities coming from the roll, pitch, and yaw. The angular velocity due to the change in roll angle is given directly by the rotational speed around the x-axis. The angular velocity due to the change in pitch angle is given by the rotational speed around the y-axis, but it has to be pre-multiplied by the coordinate transformation, the rotational matrix from pitch to roll. And the angular velocity due to the change in yaw angle is the angular velocity around the z-axis, the inertial z-axis, but it has to be pre-multiplied by the pitch roll coordinate transformation and the yaw to pitch coordinate transformation. By using the coordinate transformations from yaw to pitch and roll we have seen before, and by plugging them into the angular velocity due to roll, pitch, and yaw, we can find the absolute value for the rotational velocity in body frame by plugging them all together. So the relation is then given, as you can see it here in this matrix, as a function of the roll, pitch, and yaw rotational speeds. Based on the calculations of the previous slides, we have found a relation between the angular velocities in body frame and the tight Bryan angles. This is given through this rotational matrix ER. This rotational matrix has a singularity as plus minus 90 degrees, which has to be considered during the whole modeling. Additionally, in our case, we are only looking at the dynamic model at hover. For hover, we have very small angle, which means that we can put cosines to its on and sine towards 0. And if we plug this in the rotational matrix ER, we can see that we get the identity matrix. So in hover case, the whole dynamical model becomes quite easy. So with the coordinate transformation and the rotational speed in body frame, we have all the elements which are required for the dynamic model of the Quadcopter helicopter. So let us come back to the force and torques which are acting on the system. On principle, we have the force and torque generated by the rotors, and additionally we have, of course, also the gravity force, which is very easy, which is looking directly downwards towards the Z direction in earth frame. As we have seen before, our main forces generated by the rotors are the thrust forces. These thrust forces are actually acting in the Z direction of the body frame. Now in the hover case, the body frame and the earth frame is aligned, and so these thrust forces are then also directly acting in the earth frame, in the Z direction of the earth frame. Furthermore, we have seen that the thrust force can be calculated as a constant multiplied by the rotational speeds of the individual rotors. Additionally, we have a force which is the hub force, which is coming from the motion in the horizontal direction of the helicopter. In our case, for the hover, we have no vertical and horizontal movement, and therefore this hub force can be neglected. As a second element, we have the hover moments. They are composed by two elements. First, we have a thrust-induced moments, which are actually the moments which are induced by the thrust forces along the pitch and yaw axis. The second element is the drag torque, which is actually then generating a torque around the Z axis, and it's just the sum of all the individual torque of the propellers. Again, the thrust force and the drag torque are proportional to the square of the rotational speed of the individual rotors. In principle, we have a couple of additional moments we might have to consider. This is the initial counter torque, that's propeller's gyroscopic effect, rolling moments, and hub moments. However, in the hover case, for small angles, we can actually neglect these elements. After plugging in all the geometric parameters, the coordinate systems transformations, the rotational speeds into our dynamic model, we can start to analyze it. Here in the first step, we have a look at the rotational dynamics. For the acceleration around the roll axis, which is the x-axis, we can see that this acceleration depends on the squared difference of the rotational speed on the y-axis, plus an additional term which is coming from the rotation around the yaw axis. For the pitch axis, you can see exactly the same. Of course, it's then the rotational speeds around the y-axis. And for the yaw direction, we can see that the acceleration around yaw is directly proportional to the sum of all rotational speeds of the rotors in square. This shows us that for hover, the whole model becomes quite reasonable and the complexity is not too high, and so this allows us to find then appropriate controllers at a later stage. In a similar way, we can actually analyze the translational dynamics. We can see that all the translations in x, y, and z direction depend on one side of the cross product between the rotational velocity in the body frame and the velocity in the body frame, plus a part of the projection of the gravity vector in this direction. Additionally, in the z direction, you have all the sum of the rotational speeds in square, which generate a force which allow us then later on, as we will see, to control the z direction. In the near hover case, you can also additionally see that these angles, which are defining the projection of the gravity forces in the different directions, will become very small, and so the whole concept or the whole dynamic model will further be reduced and simplified.